Hello students, now let us go for one more experiment today, that is determination of direct axis reactance and quadrature axis reactance for the given salient pole synchronous machine. We know that synchronous machines are of two types, one is cylindrical pole and salient pole synchronous machines. In the case of cylindrical pole machine, air gap is uniform and hence the reactance offered by the armature winding is uniform throughout the air gap. Whereas in the case of salient pole synchronous machine, air gap is not uniform and therefore definitely we observe that very less air gap along the axis of the field poles and large air gap in between the field poles. So this will cause saliency in nature for the salient pole machine, and because of this saliency in nature we will be getting the reactance non-uniform. So we will be getting one reactance along the field pole axis which is maximum, and we call it as direct axis reactance. In a similar way, even the reactance in between the axis of the poles, field pole axis, the reactance will be very large, and we take that reactance as XQ, that is quadrature axis reactance. So how do you determine this XD and XQ experimentally? So we will see that experimentally right now by conducting a slip test on alternator. So the circuit diagram for the slip test is shown here. It is seen. So this is an alternator where we can see R, Y, B are the terminals of the three-phase winding, and X, XX is the field winding terminals. So since this is a synchronous generator, that is alternator, and that too we need to consider salient pole alternator. So this alternator is to be driven with the help of a prime mover. Hence a DC motor is considered here, the prime mover. And you can observe this is the circuit diagram for starting the DC motor, which acts as a prime mover here. So from plus terminal as usual, which I explained in the previous experiment, straight away we will go fast that from plus terminal the connection is given to L, and LL is connected to the negative of the DC supply, and F terminal from here it is connected to one fixed terminal of field rheostat, and the other fixed terminal is kept open, and from the variable point it is connected to Z, and ZZ is connected to the negative, and again from armature that is A of starter, 4-point starter, it is connected to AA, and then AA is connected to negative terminal. So this finishes the 4-point starter diagram connection to the motor, and that finishes off the prime mover connection. Now coming to the alternator, we need to measure the armature voltage and armature current. Is it clear? And in order to observe the saliency nature of this alternator, we need to give a reduced voltage, and the machine is to be run at a little less speed, that is little almost we can say 10 to 15 rpm difference to that of synchronous speed. So we know that alternator is to be run at its synchronous speed. So here in our case the synchronous speed of this alternator is 1500 rpm. So we need to run this machine a little less than that of 1500 rpm, like we can say 1485 rpm, or a little above rated speed, that is we can say either 1510 rpm or 1515 rpm, like that. So in order to run this machine at a little lesser speed or little above rated speed, so it should be driven with the help of a prime mover. So these alternator connections are as shown here, and one important aspect is the field winding should be kept open. In order to see that, it should be kept open, and one more thing is we need to check the phase sequence of the alternator. To check that phase sequence, the voltmeter connection across XXX will also give us an indication. So the purpose of voltmeter here is to check the phase sequence of this particular RYP with respect to the input voltage. One more aspect, we are also giving supply to this alternator through three-phase variac or through three-phase auto transformer, and the supply that is given is almost we can say that 25% of the rated value. When we give that a little less voltage, and the machine if it is run at a little less than that of synchronous speed, then we can observe clearly the saliency nature of this alternator. Is it clear? So the phase sequence of the supply and phase sequence of the alternator both should be matched, and that can be observed by this particular voltmeter. If the voltmeter gives a deflection, if there is a deflection in the voltmeter, it does mean that phase sequence is not matched. So then we can reverse any of the phase terminals of this alternator, and then again we can run it so that voltmeter across reads 0. So if voltmeter reads 0, it does mean that phase sequence of alternator is matched with that of phase sequence of the supply voltage. So this is the auto transformer, and ammeter is connected from R, and the other end of ammeter is connected to the variable point of one terminal for the auto transformer. Similarly, voltmeter common terminal is given to the ammeter other end, and voltmeter another terminal is connected to the neutral. So the voltmeter that is connected here indicates the phase voltage, not line voltage. So this is the three-phase variac, and three-phase supply connection is given to the three-phase. So three-phase input is given to the auto transformer, and output is given to the alternator, and that output is variable alternator or variable voltage. So this is what the explanation for the circuit diagram. Once if we are thorough with the circuit diagram, then let us go for naming or giving the ranges of ammeter and voltmeter. From the nameplate details, we can observe the nameplate details of alternator as shown here: 3 kVA, ampere rating 4.2, and volts rating 450, and RPM is 1500 RPM. Similarly, the shunt motor ratings are shown here. So here we are concentrating only on alternator, hence we are not going to concentrate on nameplate details of shunt motor, but we can note down that in the observation. So these are the nameplate details. So once if you know the nameplate details, then since the machine is to be operated under no load condition, no load or even whatever the load, whatever the condition that we are going to take, so ammeter range should be 0 to 5 amperes, because the maximum current rating of this alternator is 4.2 ampere. Therefore, the range of this ammeter should be 0 to 5. Whereas voltage rating that we are going to consider is actually the nameplate details is showing 415, that is the terminal voltage. But if you take phase voltage, it will be something around 239 volts. And since we connect this voltmeter across the line and the neutral, so this value will be showing us only phase voltage. And we are not applying the rated voltage here. We are applying reduced voltage, approximately 25 to 30% of reduced voltage. Hence, instead of connecting 0 to 300 here, we can connect this take the range of 0 to 150 volts. And of course, the type of meters are for both ammeter and voltmeter are moving iron instruments. So after finishing off giving the nameplate details and then considering the ranges for the ammeter and voltmeter, so let us go for the connections. Okay, now voltmeter and ammeter ranges are as shown here. Now another voltmeter is there across X and XX. This is X and XX, nothing but the field winding of alternator. So the range of this voltmeter is to be taken as 0 to 600, because the supply voltage that is given to the alternator three-phase voltage, if by chance sudden rated voltage is applied, then in that case maximum voltage that is induced in this field winding will be something around 400 volts. Hence the range of this voltmeter is to be taken as 0 to 600, and of course moving iron instrument is to be considered here. So once if we fix all the ratings of these ammeters and voltmeters, then we go for connecting the circuit, giving the connections as per the circuit diagram. First we will see the motor DC motor connections, that is prime mover connections. See here, from plus terminal it is connected to L, and from AA connected to A, that is A of starter to armature terminal of DC motor, and from field terminal of starter it is given to the one fixed terminal of field rheostat, that is this is the field rheostat, and it is kept at minimum position because the current enters here and then flows through this variable point and directly goes to the second variable terminal which is connected to Z. That means this resistance is not included in the circuit. Therefore, we can say that it is at its minimum position. And from ZZ, it is connected to negative, and A is also connected to negative as per the circuit diagram shown here. AA, ZZ, L, all the three are connected to negative. You can observe LL, this is LL, and this one is AA, and this one is ZZ. All these three are connected to the negative terminal. Is it clear? So that finishes the DC motor connections. That is the prime mover connection. Next, as I said that voltage across the field winding is to be kept open. So that means what? Simply we can connect a voltmeter as shown in the diagram, that is this voltmeter. You can observe this is X and this one is XX. So where we take this as alternator field winding, and across this field winding a voltmeter is connected here. The purpose of this voltmeter is to indicate whether the phase sequence is matched or not. If you get any reading in this voltmeter, it does mean that the phase sequence is different. So that we need to go for changing of any of the two terminals of the alternator. Therefore, we can maintain phase sequence same. So the range of this voltmeter is taken as common and the range 600. So once field winding is kept open, then let us go for giving input to this is three-phase variant. That means three-phase auto transformer. The input to this auto transformer is from ABC supply. That means direct three-phase supply is given as input to the auto transformer, and see that this knob should be at its 0. That means output should be 0 value. From the output, these are the output terminals. From the output, you can observe they are connected to alternator terminals as shown here. That means from R. See here R, Y, B are the three terminals of alternator, and N of M is the neutral of the machine. From R, we can observe two wires are taken here, where they are connected to, one is connected to ammeter, that is 0 to 5 amperes. Another one is connected to voltmeter, that is common terminal. And since we have gone for, since we are applying the reducer voltage, so better we can give this to 150 volts instead of giving it to 300. So students, please do remember that the connection should be very tight, or else the conduction will not be smooth. So once if this ammeter and voltmeter both are connected, see here common terminal and 150 volts. So the other end of this voltmeter is connected to neutral of the machine. The other end of this ammeter is connected to one input terminal, one output terminal of three-phase variant. Other two output terminals, if you see here, Y is connected to Y. Actually, it should be Y. Y is to be connected to Y, and B is to be connected to B. See here, Y is connected to Y, and B is connected to B. So this is how the connections for the slip test. So once if you are thorough with the connections, then we need to go for conduction of experiment. So let us see the conduction of the experiment. That is, first initially we need to give the supply, that is by closing the DPS to switch, and then start the DC motor slowly with the help of a 4-point. So the DC motor is started, and let us observe the speed of this machine. It is to be should be run at nearly 1500 RPM. So it is showing 1426. So let us check 1485 here. It is 1485. It is running around 1485, 86 RPM. So once if we run at this particular speed, then start giving supply to the auto transformer. So that is by closing the DPS switch. So DPS switch is closed, as shown here, and we need to give a reducer voltage across the armature terminals. You can see here, slowly I am increasing. So reducer voltage, how much of reducer voltage means 25% of rated. Since we have connected voltmeter across neutral line and the neutral, rated voltage will be 230, and 25% of 230 will be something around 57 volts. So approximately you can apply 57 volts like this. And see here, the voltmeter connected across field winding terminals is showing 0. It does mean that the phase sequence of alternator and phase sequence of three-phase input, three-phase supply both are matched. Once if the phase sequence is matched, then slowly we can conduct the experiment here. Please observe. After giving reduced voltage, we need to measure the speed again, because we need to run the machine at a reduced speed, something around 1485 or 1490. So before going to that, please check it. See here, the speed of the machine should be just reduce it now. Okay. Yeah, you can observe the speed is something around 1482, 83. And at this particular speed, please just observe the vibration, oscillations of both voltmeter and ammeter. And even if you run at least 1490 also, you can observe the clear cut oscillations of ammeter and voltmeter. Please observe, the voltmeter is also getting deflected. At this condition, that means we need to find, or we need to measure the maximum deflection of this ammeter and its minimum deflection, as well as maximum deflection of voltmeter and also its minimum deflection. So once if you observe these oscillations of both meters, once you observe the oscillations of both the meters, then we need to note down the ratings. So readings of both ammeter and voltmeter. So the readings are noted as shown in the tabular column. So first serial number 1, speed 1485 RPM. First reading 1485. Then voltage, minimum voltage. Please wait for a time to observe the minimum voltage. So the minimum voltage it is showing is 56 volts and maximum voltage it is showing is 58 volts. So it is showing 58 volts, 59 volts maximum. And similarly, the current minimum and maximum. So you can observe the maximum current is 2.8 and minimum current is 2.2. Since it is connected to 5 amperes, please see here, it is connected to 5 amperes. Whatever the reading that we get here, it should be halved. So the value should be halved. You can see here 2.2 by 2 and 2.8 by 2. So that finishes taking the reading, one reading for this experiment. Similarly, we need to go for slightly change the voltage. Slightly change the voltage. 3 readings we need to take and then average value we need to consider. So slightly I have changed that voltage, and please see that the speed should be at the same value only. The speed should be again 1485. The speed should be, you can observe, 1485. Okay, 1490. 1492. Okay, 1485 we need to consider. $1484.85. So after getting that speed around 1485, again we need to consider the ratings here. Maximum voltage rating 61, minimum 59. Similarly, current maximum 3, minimum 2.3 by 2 again. Similarly, another voltage you need to apply, slightly change in that voltage, and you need to see that the speed should be again the same. Maintain the speed again at 1485 RPM. So after maintaining 1485, again note down the readings. Maximum voltage 65, minimum voltage 63, maximum current 3.1 and minimum current is 2.4. So you can observe the tabulated values are shown here for one particular speed little less than synchronous speed. That means 10 RPM or 15 RPM difference should be there. So if you make the machine to run at 1500 RPM, we cannot observe the saliency nature, and even we cannot see the oscillations in both the meters, that is in both the voltmeter and ammeter. Only that difference in speed is, if it is very less, like 10 RPM difference or 15 RPM difference, then definitely we will be getting the saliency nature. This can be observed experimentally. In a similar way, even this slip test can be obtained, can be conducted even above the rated speed also. So now let us see the rated speed, 1480 RPM, 1510 RPM. I am just considering 1510 RPM. You can observe, okay, 1515 RPM you can observe. So for 1515 RPM, maximum is 65, minimum 64. Current maximum is 3.1 sorry, and minimum is 2.6 by 2. Just reduce or take another lesser voltage, and the speed should be again the same. It should be 1515 RPM only. So 1515 RPM, same again. Maximum voltage 60, minimum voltage 58, maximum current 2.9, minimum current 2.3. Similarly, at another value, again we need to see 1515 RPM. Then note down the readings again. Maximum voltage 54, minimum 53, maximum current 2.6, minimum current is 2.2. So like this, 3 readings can be taken at one particular speed, and that is below synchronous speed. Another 3 set of readings can be considered at above speed, little more, that means 10 to 15 RPM more than that of synchronous speed. So once if these values are noted, then we need to calculate xd and xq, where xd is equal to from the procedure you can observe xd is equal to maximum voltage by minimum current, and xq is minimum voltage by maximum current. This should be calculated here. V max 58 by 1.1. So where we can get you can observe xd value divided by 1.1, 58 divided by 1.1, something around 52 ohms, 52.72. Similarly, xq 56 by 56 divided by 1.4, it is 40. You can observe 40. So like this, for every day reading we need to tabulate here, and average value of this is to be noted down. Okay, now we are turning off the machine. See here, 3-phase supply to the auto transformer and DC motor is to be removed. So with that, experiment is finished for this determination of xd and xq from that is for the given cell and pole alternator. Now you can see here we are calculating the values. So all values are tabulated. See here, for the second reading, the values are obtained as 54.2 and 39.3, both xd and xq. Because slight variation will be there for every change in the voltage, so you need to take the average. You can consider even average of 2 or average of 3, no problem. But here we are considering average of the 3 readings. Similarly for 1515 RPM. I think this is enough, ma'am. So now average of, let us calculate average of 3 readings xd, 52.72 plus 54.72, sorry 54.2 plus 54.16. 54.16 divided by 3. So you can write xd average, that value is average by 3 divided by 3 gives us 53.6, something around 53.69 ohms, that is xd value. Similarly xq value. It is 40.43 ohms. Dear students, you can observe that xd value is always greater than xq. Even theoretically, it is shown that xd value will always be greater than xq. So that finishes the experiment on how to determine xd and xq for the given cell and pole machine. So since this particular test is conducted at a slip speed, this particular test is known as slip test on cell and pole alternator for determination of xd and xq. So that finishes determination of xd and xq experimentally. That's all. Thank you very much.